So I grew up in Cape Town next to an Italian family. So we were a German family next to an Italian family. And we got on really well, except there was one day where we didn't like them very much. No, 1982, July the 11th. But besides that, we got on very, very well. So let's have a look at java.lang.String. Let's have a look at this. Here we've got a little way in which we convert an int to a string. And the question is, which is the best way? What JDK? That's a good question. Okay. What JDK? Good question. No, it's actually made it worse. Okay. Put this off. So one way is you can just do the lazy way, double quotes plus the val, which of course you should never do because you shouldn't be lazy as a programmer. The other one is integer.toString, there's integer.value off, then string.value off, and integer.getInteger. So who says the first is the fastest way? Let's say Java 12. Let's take Java 12. Why not? Have you used Java 12? Okay. Who says the second is faster? No one. No one? Who says the third is the fastest way to do it? It's got to be somebody saying the third. Come on, somebody. Okay, brilliant, thank you. Who says the fourth is faster? Okay, we're getting a bit warmer, fantastic. And the fifth one? Fifth one? Okay, nobody good. Another one, another silly question. These are all silly questions, just to get us thinking a bit. Which is the fastest way to append strings together? So the first one, I'm using plus, which of course can't be fastest because it's the shortest. Fast code has to be long and verbose. The second one, I'm making a string builder, and I'm sure if you've worked with code long enough, you've seen code like that. And the third one, you see, the thing is when you use string builder, you're making new char arrays all the time. So the third one, we are first working out how big is the array supposed to be, and then we add all the strings together. So who says the first is the fastest? Okay. Which JDK? Okay, anything after Java 7. Java 7 and afterwards. Who says the first is the fastest? Okay. Who says the second is the fastest? Okay, good, very good. Who says the third is the fastest? Okay, now who didn't put up their hand? Anybody didn't put up their hand? Please put up your hand up. Okay, you're right, thank you. So they're all the same, exactly the same. And the reason they're the same is because, I won't tell you now, we'll tell you later. Okay. Now I want to go back to history when the dinosaurs roamed Earth, Java 1.0. Okay. And in those days, they actually started by saying private char value square brackets. You know, these were C programmers. And in those days, when they had a hash code that was bigger than 16 characters, they made samples of it. So basically looked at every X number of characters. So, no, sorry, that's wrong. They looked at only, I think, 30 characters of it. It was like a sample of all the strings. And it was obviously it wasn't a very good hash code at the end. Because if you had several big strings, they would have almost very, very similar hash codes, all the same hash codes. And some other things like equals didn't check if the objects were actually the same. Intern had a static hash table, which happened to be a memory leak. And a string buffer was basically your modifiable string-safe version that you could use for changing once you had constructed it. Now, when you called toString on the string buffer, what was really cool with that was that it shared the same underlying char array. So we didn't have a new char array being made every time we called toString. So this was some of the magic that happens. Brilliant. And if you look at the way that the source code, if you look at the Java source code nowadays, you'll see that in the Java source code, when you say toString, it makes a new array every time you call it. We'll get back to that in a moment. This is what the hash code looked like in string.1.0. You can see that if the length is less than 16, it actually adds up the numbers with a multiplier. Otherwise, it looks at only 8 of the characters. It says the skipper's length divided by 8. So it only looks at 8 of the characters. If you have 1,000 characters, it only looks at 8 of them to work out a hash code. And, oh, by the way, this is Dimitri. Dimitri is a software engineer. He's our chief troublemaker, disorganizer at jcrete. He was trying not to come. He tells me that he hurt his leg skiing, but actually last night he got beaten up because he asked for a Hawaiian pizza. Right.
Yes, and this is Heinz Kabutz, the troublemaker, the creator of jcrete.conf and Java Specialist newsletter, and we'll try to entertain you with the string history here.
Yeah. So, just by the way, if you're not on the Java Specialist newsletter, please join. Also, I've got a surprise gift which will sort of not work after 7 tonight. So if you look at that after 7, you'll get a not so big surprise gift. If you do it before 7, you'll get a big surprise gift, but after 7 won't be as great. So that tiny-year-old Vox Milano 19, have a look at that if you want. You'll get something if you do. The link's also here on the side. As I said, it changes after 7 tonight. You know, once the beer starts, the gift diminishes significantly. So, Java 1.1, they changed things a bit. First of all, the field stayed the same, and the hash code was still sampling. They moved the intern to some native code, which wasn't necessarily going to be better than Java. And yeah, so it also had some weird stuff like to uppercase, had some weird edge cases, like the German SZ became 2 big S's. So the length of the string could change when you did to uppercase on it. Kind of weird. In Java 1.2, the field stayed the same, but they changed the hash code. And that was the last time they dared to do that, because the backlash, you can't imagine. I mean, even 1.2, there were already so much legacy code out there, and people are like, my unit tests are not working anymore, you know? Martin was talking about crybabies. There were a lot of crybabies in those days. And so what they did was instead of counting only 8 characters, they added up all the characters. And it broke a bunch of tests, which was probably not such a bad thing. Also, they added a comparable interface, and we'll get back to that a little bit later, what that means. Now, the performance in the past was constant time performance. So it didn't matter how big the string was. It took the same amount of time, constant time, in other words, not the same, but constant time, to calculate the hash code, whereas it changed to linear time. Now, of course, we all know what that means. It can become significantly slower to calculate the hash. And so the book was written called the Java Performance and Idiot Guide. No, sorry. Idiot. The idiom guide, right? Anyway. Now, it was a good book when they wrote it. But performance books, they've got a shelf life of about 3 months, right? Until the next Java version comes out, and then you can throw them away. Well, you sort of. It's a problem. And they wrote a good book, but and sort of one of the biggest arguments in the book was you should always cache your hash code. So you must never use string as a hash code. You always have to put string inside an object and then cache the hash code. And shortly after they wrote the book, Java 3 came out, and they cached the hash code, right? Now, the thing is that the idea with caching the hash code doesn't actually help us that often in many cases, because the whole point of a map is to put things in which you can get back later. So you put in the value, you throw away the key, and later when you want the object back again, you regenerate the key and you find the value again. That's sort of how a map works, how it's used. And if you look at this, here I've got a hash code which takes 100 milliseconds just to make it really slow. And actually, the amount of time it takes to put 30 elements and get them is exactly the same whether you cache or not cache the key. It really does make a difference. Because inside, the hash map is going to cache anyway, the actual hash code value. So it really doesn't improve it that much. But anyway, they added this thing called the hash. And what was interesting is at the time, the memory for that hash was free. Okay? On a 32-bit machine, at least. Because the value was a char array, and that's 4 bytes. The pointer to the char array was 4 bytes. then int is 4 bytes, offset count and hash each are 4 bytes, and it allocates anyway in multiples of 8, therefore it basically was for free having putting the hash in there. It was in those days. Of course, depending on what you're running on, it's 32-bit, 64-bit, compressed oops or not, it'll make a difference. But in those days, it was actually for free. And you know, we all know that string is immutable. In fact, they even say that in the documentation. It actually does change the hash internally. When you call hash code, it changes the internal state. It's not visible from outside, and it's a data race, which is a benign data race, because the result will be the same no matter how many times you call it. So there is a data race, but it doesn't matter, because in the end, the value is still going to be 42. So it doesn't matter which way you call it. Now, if you look at these strings, this is some Ukrainian which I found somewhere. It's a telephone directory from the Ukraine, right? No, okay, it's not. So, what was it?
Hungarian, maybe.
Hungarian. That's too short. The names are too short. So, what do these strings have in common? The hash code is 0, right? So the hash code is always 0. Each of these strings, the hash code is 0. And if you want to know how I found them, well, okay, there's an algorithm that somebody wrote. Can't remember who it was. Somebody really famous, and I don't remember his name now, so it's really... No, it was Mark Reinhold, I think. I think it was Mark Reinhold. Somebody really famous wrote an algorithm where he reversed a hash code. So if you want to have a hash code of 25, you say, I want the 25, and it generates a string for you with the hash code 25 by simply going in reverse to get to the hash code. So, I tried using the algorithm to generate strings, but the problem is it will give you a string with the number, but I wanted to find lots of strings with the hash code of 0. So I just did it brute force. I apologize, but it did work in the end, doing it brute force. And so here, the interesting thing with these strings is they all have hash code of 0, and if I add them together, any two together, or even the same one together, the hash code is again 0. Because once you get to 0, you start from the beginning. You get back to 0. So the interesting thing with that is because they've got the hash code of 0, any combination of these strings also gives you a hash code of 0. And let's have a look at why that is so bad. I'm going to look at different versions of Java. And let's get back to the IDE. Oh, I'm echoing myself. So my neighbors in South Africa were a little bit shorter than the German neighbors. And so I see why this is so low here. Let's try and get this working. Okay, so here's the code, as before. And it's basically, I've got the 0 hash codes, and the 0 hash codes, just a few of the strings, and then I simply combine them together. You can have an infinite number of strings generated, in fact, practically generated, with hash code of 0. So, so what I'm going to do is I'm going to run this, first of all, with Java 6. Okay? And here's as you see, as I double the number of strings, and it's actually not that many, and every time I make it twice as much, the speed gets also approximately twice as slow. So you can see that the hash code lookup, so we went from about 1 second to about 2 seconds. This is roughly roundabout. So so what you can say is that this actually, the hash code lookup, the hash code, to find the value, even though the hash code is cached, ends up being linear. Now, the problem is not that the hash code is cached or not cached. The problem is that all of the strings end up in the same bucket inside the hash map. Right? That's why we end up with a linear lookup. And it's going from...
The hash map degrades to linked list.
The hash map degrades to linked list, right, in Java 6. Now, something went wrong. Probably we exceeded some size where things are not happy anymore, but it's generally going to be linear. Now, in Java 7, they actually did something which was quite interesting, and they wanted to stop this from happening. They wanted to stop people from attacking web servers by sending the same string over and over, well, not the same string, multiple strings which all have a hash code of 0, and then somehow ended up inside hash map and degrading the hash map. And so, as we saw with Java 6, it became a problem. Now, Java 4, now of course I don't have Java 3 on my machine. In Java 4, the fields were the same as Java 3, and they introduced the char sequence interface so that you could either speak to char sequence or to string, and they also had regular expressions, which are also not the fastest. You'll talk a bit about that, I think, when we get to the format, maybe mention that. Now, of course, in the past, when you added strings together, like hello plus arg0, it would generate a string buffer, and then call .append args0.2string. And this new string buffer would, in the Java code, make an array of 16 characters. In Java 5, the fields are the same as Java 1.3, but they mark them final, except for the hash, which, one should always try and mark fields final, where you can. And they had code points, so a character could actually be a combination of 2 characters. We had also the StringBuilder, which was an unsynchronized version of the string buffer. And the char array would no longer be shared with created strings. Now, the thing is that when we went from Java 4 to Java 5, we had to actually recompile the code to take advantage of this new feature. I actually, at one point, I was working with a library, and I changed the string plus, with just normal plus appending, to use string buffers with a preset size, because it did make a noticeable difference in the performance. So I shaved off about 10%, and I made it about 10% faster with that optimization when it went back in Java 4. So the problem is that optimization actually wouldn't work Java 5 onwards, because now it's no longer string buffer, it's string builder. So you actually have to go back and change your string buffers to string builders and recompile all your code. Okay. Java 6, nothing much changed in the structure, but they did add this feature of compressed strings, where sometimes a string would use a char array and other times a byte array as a foundation for keeping the characters, which was kind of weird. If you're working with reflection and you look at the string, and sometimes it's a byte array and sometimes it's a char array, things got funky. They also added optimized string concat at some Java 6 version, which meant that your char array could at that point also be shared between your string buffer, string builder, and string. So remember when I first showed Java 1.0 that they shared the char array between the string buffer and the string? That happens automatically from Java 6 onwards. So if you look at the Java code, it doesn't happen, but in the real world it does happen. So that's quite cool. Here's so the first benchmark. We were adding only strings together. And when you're only adding strings together, it doesn't matter which way you do it, it's exactly the same speed. So when you look at these values, the append basic, that was just with plus. Append string is with a string builder, and append string builder with the size. You notice that they create the same number of bytes. 208 bytes, Java 7, 200 bytes, Java 8, 200 bytes, Java 11, 120 bytes. We'll talk more about Java 11 versus Java 8 in a moment, and that includes Java 9 as well, why that's less. Java 7, I mentioned to you that they were concerned about the possible attack on servers by having lots and lots of strings of hash code of 0. So they solved that by having another hash code. It's called hash32. Now, when I saw that, I got really excited. I thought, awesome, now all my systems are going to be faster. And I used it for many years without realizing that it doesn't work until you explicitly turn it on, right? I only realized when I was preparing this talk, I was like, oh, so it wasn't ever used, right? So the good thing with having hash32, it's still a linear cost, but they use some randomization to stop you from being able to make always the same hash code. And their default is hash of 1, not hash of 0. So if it's not initialized, it's going to be hash of 1. So it helps a lot. So if you run this with Java 7, let me just quickly copy this over. Put this on my So if we go back to our test here, run it in Java 7, the first version is going to be exactly the same as Java 6, also linear degradation. As we double the size of n, it gets about twice as slow, approximately. You know, obviously, there's some bumps in the road, but that's sort of what happens. And then if I add the field, sorry, that environment variable, then, okay, let's put this in here. Now look at the performance. It goes, it first gets worse. Once we get over the threshold, then it starts using this int32. So once it gets past the 256, it uses this int32, and then it gets a bit faster, I hope. Oh no, I've done something wrong. Am I still using Java 6?
You have to recompile, I guess.
No, I don't have to recompile it, I don't think.
Are you sure?
I am sure, but I might be still using Java 6. Or maybe I got something wrong. I did something wrong. Not quite sure what.
Oh, it's a demo.
It's a demo. It's supposed to not work. And I shouldn't have to recompile it. Almost certainly not. I'm going to recompile it just to make sure that. No, that's. I'm not going to do that. Threshold. Oh, of course. I've got the flag in the wrong place. So it's simple stupidity. So it should have been at the beginning. So you see what initially it runs, and then once it gets past the threshold, it really speeds up, right? So the hash map lookup is no longer linear because you don't have a linked list of elements as keys. But you had to turn it on explicitly. If you didn't do that, you didn't have any of these benefits. And again, the reason why they didn't want to do automatically is because people would complain that their tests don't work anymore. All right. And also there was another constructor which we could abuse, which we passed in a char array and Boolean unshared. Now this was this method was package access, but you could access it with shared secrets.get java.lang.String unsafe with a char array. And that would then use the same char array as you pass in for the string. So if you wanted to minimize on memory usage, you could do that. Now they've moved that out of harm's way for Java 9, and it wouldn't really work Java 9 anywhere because now they've got byte arrays instead of char arrays. Another thing which they changed was the substring in the past used to return a new string that pointed to the same char array but with different offset and length. And they changed that to be a new char array every time, which caused issues for quite a few companies where and you can easily get around that by making your own subbable string, but it's a bit messy. So that's pretty.
But they did that to avoid memory leaks. But the whole reason to remove that was to avoid memory leaks. If you get a big XML document which is 1 GB and you take user ID or something out of it, you still have a pointer to the original array. So you leak in memory, even though you think you just have user ID. That was the reason to remove that. By the way, Java is not the only runtime that had this. So V8, for instance, from Google, they had this optimization, then they removed it and they put it back because users complained. Well, JavaScript. They can have memory leaks, you know.
Yeah, so nobody can be happy with both options. You know, somebody's always going to complain. Doesn't matter what you do. Okay, Java 8. They've got the value is a char array, an int hash. They got rid of the hash 32 again because they solved the problem with the linear performance of a map in a general way. And what they do with hash map since Java 8 is as soon as you have too many collisions, they actually create a binary tree. In order for that to work properly, your key has to be or should be comparable. This is why since Java 8 you should always make all keys hash code equals and comparable so that you can take advantage of the great performance improvements you have Java 8 going forward. Also, you've got the option of deduplication of char arrays, and I'll show you that in a second, but I want to run that test again with Java 8. So let's go to Java 8. Java 8, and this time without any sort of funny settings, straight off the box, you can see that as we increase the size of map, the performance does not degrade as badly as it did before. And here, all the elements are still in the same bucket, but it's a binary tree now. So it's degrading with order log n or whatever. I mean, it's, yeah? Yeah. And this behavior you'll see also in Java 11 as well. Same type of thing. Now, of course, you've got a different GC, garbage collector, so the results won't be exactly the same, but you can see the performance is not degrading as badly as in Java 6. So for example, for 65,000, elements in the map in one entry, we still, I mean, I'm doing lots of lookups, not just one lookup. It's still performant enough. Now, deduplication is quite a nice little feature. You get this in G1, not in the other GCs. I don't know why. I mean, they probably could do it in other ones as well. But the idea is that they, if you've got multiple strings which have the same content, or they're different strings, but they've got, they've got different char arrays because they've been created separately. Then before the object gets moved to the old space, the char array gets shared with other strings which have the same values. So here I'm making two strings with the same char array. So it's going to be two strings with different char arrays. You can see it here with reflection. I'm printing out get S0 and get S1, and you can see the char arrays are different. After the GC is run, now I'm quoting explicitly GC, it will happen even if you don't do that, we'll still go and do the deduplication. Before it goes to the old space, it'll do that. And afterwards, you'll see that it's now the same char array. So this can save your memory without any real effort. Well, it usually does from what I see, make things a little bit slower. So performance can be affected by it. But, and it's not on by default, you have to turn it on explicitly, and it only works for G1. But besides that, I think it's pretty cool. Now, intern has been with us for a long time, and what intern does is it gives you a string from the shared string table. And Dimitri and I gave a talk at Java 1 last year.
Code.
What was? Where?
Code 1.
Code 1. Cold 1. And at Code 1, we gave a talk, and we lied to the people, but we didn't do it on purpose, because they changed something in Java 11 without telling anybody. We still haven't figured out where they actually did that, or where they documented what they were doing. But what they did was, in Java 11, they changed the way that the intern table is structured. Up until Java 10, the intern table was a fixed size table, and was always a prime number, all the typical hashing magic there. And they changed it in Java 11 to be changing table, and also power of 2. So it starts, I think, 65,000, and then it keeps on growing as you add more and more strings, in order to reduce the amount, the number of clashes that you have inside the hash map, inside the string table. So the performance is still not great for the intern table. You can get much better performance if you make your own, for example, concurrent hash map, and use that to store duplicates of strings. But it's not as bad as it used to be prior to Java 11. So Java 11 has not changed this a bit. And Java 12 is the same as Java 11. What's changed? Okay, the deduplication will save some memory, because you're not duplicating the char array. But of course, if you've got a complete, if using intern or concurrent hash map, it will actually be saving even more memory. Now, is it over to you yet? What to do? Go for it.
Or you can put the structure.
Okay, so I'll talk about the structure. Maybe we'll talk about the results or the effects of this. Java 9, they changed the byte array. I'm sure you've heard that. They've also got a coder byte to say what the encoding is, if it's UTF-16 or or Latin 1, that's right. They don't like the Greeks, they only want Latin 1. And they also changed the way that they do the string concatenation. You remember when we went from Java 4 to 5, we had to recompile all our code. And this meant that the way they did things in the past, they couldn't optimize the code that had been compiled already by changing the algorithm. And I think now it's definitely over to Dimitri.
Yes, so let's see what we have here.
I think it's sort of the same. Okay, so the benchmarks are there.
Yeah, okay. So we did we wrote a little benchmark to show how these things affect the code road. So what you see on the screen, we have a benchmark where we add together strings with a plus, with StringBuilder, Java 5 onwards, using a string concat method, by the way that exists, and string format. And what you see, like across the versions, 6, 7, and 8, more or less, always StringBuilder was winning, or rather, plus and StringBuilder size, the plus and StringBuilder is the same because that's exactly what Java C would emit. So if you write A plus 5, the code would generate a new StringBuilder, append A, append 5. So that's why plus and StringBuilder are the same. And if you knew the sizes of your string up front, so StringBuilder sized, that was always faster. Now, if you switch and if you look to Java 11, then the plus actually wins big deal. And especially if you look at an amount of bytes allocated. So exactly here you see an interplay of two features. One is compact strings. You remember in Java 6 they added a byte array, char array thing that there was a special flag. It was retired somewhere between 7 and 8 because they realized it was not such a good idea. But what they also realized is that if you analyze the heap dumps in general, lots of stuff, about 25% of things in the Java heaps are strings. And majority of the strings are Latin 1 encoded, so it's basically ASCII plus Latin 1, a couple more characters. But the thing with Latin 1 character set, it fits in 1 byte. Java used to have strings always UTF-16 encoded, which means need 2 bytes. That's why we had character array. So with Java 9 Plus, that is replaced. So even on the Java source, there is no more character array. It's always byte array, which brings a couple of interesting things.
Before you go on, just the question I asked we also at the beginning was a bit different to this benchmark because in the quiz we only appended strings together. And in this benchmark we mixed parameters. We had some int, I think
int longs.
Int long, double, I think, not double, but at least we had some numbers and some strings together. And when you're mixing the parameters, then it does make a difference if you're using plus or StringBuilder sized or StringBuilder. Then it actually does make a difference.
I just want to mention one more thing. If you look at the string format down there, it's just horrible. It's like 15 times or 15x loses to the plus. Well, all is not lost. There is a JAPS 348 and currently in candidate state. It's not slated for any Java release yet. But what they want to do, they want to intrinsify the string format. So essentially turn the string format call into something like string concatenation. Because the problem with string format is that first you get a format string, which you need to parse to see where the arguments are. The arguments that you pass to string format need to be boxed into objects. The array needs to be allocated, and there's a lot of overhead. And for example, string concat now can take advantage and do stuff without allocating objects. We're going to talk about it later. So, string concatenation. Starting with JDK9, JEP 280. As Heinz mentioned, the problem with string concatenation, it was a Java C feature. So every time you compile code, Java C would emit bytecode. And the JIT would have to live with that bytecode forever. So they tried to optimize certain things. They did a lot of stuff. Then they realized there's too much effort to support JIT to have optimized strings. So what if we do something different? What if we compile strings to a point which we emit different bytecode and let the VM optimize it? So starting with JDK9, actually, if you, I don't know, do we have a slide about Java P output and how this compiled? No, this slide. Okay. Anyways, so what happens at the bytecode level? So if you compile, so first of all, you would have to recompile the code. You would not be able to take advantage of new string concatenation unless you compile with, well, let's say, with Java 11. So what would happen is that you would have invoke dynamic instruction emitted in the code. And invoke dynamic, for those of you who doesn't know, is basically like it's a two-stage process. So when it's getting called, it first needs to call the bootstrap method to know what do I need to do. The bootstrap method returns at the call side, and from now on, it will always call this call side. So they basically use a feature that was added originally for dynamic languages, that was later on used from Java 8 for lambdas, and now in Java 9 we use it also for string concatenation. So this thing is getting more and more used throughout VM, and it actually brings the superpowers. If you look inside of the actual bootstrap implementation, there is a string concat factory in JDK and Java.lang. There is actually 6 different strategies to concatenate strings. So there are roughly 2 groups. One is the bytecode generated based on the StringBuilder. So it's basically bytecode to generate StringBuilder like it was before, or it uses the method handles all the way down. And there are different variations where they all use StringBuilder, but the default one is different. So the default one is not allocating StringBuilder at all. So what they do instead, they say, okay, you're concatenating something, at the end, you're going to create a string. String going to have a byte array. So why not, we just allocate the byte array and write bytes into the byte array. And when they create a string, they will share the byte array with a string. So there will be no extra copies whatsoever. So the numbers you saw there, like 150 bytes and whatever, that's exactly the number of bytes that concat needs to do. There's not a single byte wasted. So, and I find it pretty awesome. We have now a benchmark to show the difference between the things. You see the default one is the fastest, and then we have different variations of wins, but I don't know who would ever change the concatenation structure. It's probably just like a kill switch, so you can, if it has a bug, so you have an option to fix the bug without installing the new. All right. So now back to the byte thing. So as I explained about compressing char to Latin 1, there is a kill switch, compact strings, which you can disable that. Actually, it's interesting. During development, they had a bit catch-22 problem because compact strings is a command line flag, and command line flags are strings. Now, you are inside a string class, and you need to look up a command line flag. So that doesn't work. So they had to do something really weird to be able to solve the problem, where they have a constant which is not a constant that is replaced by VM, because there is no other way of doing it. They try to use unsafe and everything else, but the string is so important to the JVM startup that we just crash VM every time they try different things. If you're interested more, look up Alexei Shiplev's talk on that. He goes into detail how they fight the VM to just have something like this stupid flag. So now it's back to our benchmark and just the effect of having and not having compact strings. And if you see the plus up there, we see the difference in the bytes allocated, if the strings are compact or not compact. It's not exactly 2x, as you would think, because a string object has pointers to the array and hash code and other stuff, so there's other things around it. But the more memory is allocated.
I just want to quickly butt in there and say there's this to me feels a bit Volkswagenish, because some tests I've done seem to indicate that it actually does make a difference in performance if it's at least between Java 8 and Java 9 with having these compact strings, that it can't optimize as much. But so far we haven't been able to write a benchmark. We tried quite hard to write a benchmark to prove that it is a problem in Java 9. But it's almost like, somehow there's something going on that they figure out that we're testing it, I don't know. And, right. Emission testing is going on. So,
there are some interesting edge cases. First edge case is the maximum size of the string. So if in JDK 8 you allocate, essentially you can say new character array, integer max value -2, that's a maximum array size in Java. You can create a string of that size. So it's 2 billion elements array. Well, in JDK 9+, you can't, because you have a byte array. So it's still 2 billion elements of bytes. And now here's the trick. If your string is compressible, you can do that. Your code will work. If your string is UTF-16 string, you need twice the size of the array, and the array is half of it. You will get a funny out-of-memory error saying, you cannot allocate that big of a string, and it gives you 1 billion thing, the max value it can be. That's first thing. And second thing, certain operations like substring and other stuff might get into trouble because you walk in, when you, for instance, go from compressed and uncompressed things, but I'm going too much into detail.
No, that's good.
So let's talk about, yeah, you go on. No. Intrinsics. Why do we talk about it? Okay, yes. So another thing, if you look at strings and Java code in general, there's this thing called intrinsics. So certain operations in Java, you see that there is a Java code for them, but it's actually not what JVM is executing if you run them. This is just a list of some of string-related intrinsics in JDK 8. And if you look at 11,
it's far more.
Yeah, it's far more. Well, the reason, we basically doubled all the overhead of string working. So before we just had one string class, now inside there is like Latin 1 and UTF-16, so we doubled that, and there were more intrinsics added to that. Now, there is another interesting thing. If you look in JDK 9+, how equals is implemented, for example, there is this check at the beginning, and then if it's string, first thing they do is they compare coder. So this is a special case. If you have two strings of different encoding, they by definition cannot be equal. So this is a short circuiting saying, okay, if you compare strings that are not of the same encoding, we can skip that thing. And then they check what is the common encoding and call one of these methods. So to make a point about intrinsics, let's look at how one of these methods is implemented, like Latin 1 equals. So basically we just walk the array element by element. If you find that they're unequal, we stop. Otherwise we have to walk all the array to the end. See this little annotation, hotspot intrinsic candidate. It tells the VM that this code should be potentially replaced with something else if the something else works on this particular platform. So this is platform dependent, and there's some other things come into play. And yeah, the reason we show the RS mismatch is like yet another way to do that, starting with JDK 9. So let's measure the performance. So if we call string equals with different lengths of the strings, it's basically, it's fast, right? It goes linearly with string, but it's fast. If we do it manually, like they did it in the, like walking the array manually, you see that it degrades way faster. So we have some performance problem. And if you use some new arrays mismatch stuff, it's almost as close to string equals then. So what we see in the play is actually the intrinsics. So the code that we saw on the screen, we copied it and tried to run that, but it's not the code the string equals is using. The code is replaced with vectorized loop. Essentially, instead of walking every element at a time, 1 byte, they walk 8 bytes in strides of 8 bytes. So you basically get the chunks and you go through memory faster.
Yeah, so the one thing which is interesting is that they don't actually take account for deduplication, right? So in the equals, it would make sense to see are the arrays the same. If the array is the same instance, you can just say return true in the current string structure. So that would speed things up if you're comparing equal strings. Just a few lessons from today. Use plus instead of StringBuilder wherever possible, and you'd have to recompile your code to take advantage of the new features we've got there. Also, if you use intern in your code, and I've seen code bases where they use intern extensively, rather see if you use your own cache, because it can be many factors faster. Even with the improved Java 11 version, we found it to be many factors faster to use your own concurrent hash map, especially if you don't have too many strings. It can make a big difference. Hashing can be expensive on strings, especially if the hash resolves to 0. There's not much they can do about that. They can't change the default value of hash because that would produce a data race on the string itself, which would be quite dangerous to have. String absolutely cannot have a dangerous data race. It can't happen. Also, since Java 9, we've had byte arrays for strings, not char arrays. Just remember when you're looking at your profiling that you're looking for byte arrays for strings, not char arrays, since Java 9 onwards. We've got the benchmarks on my GitHub, Kabutz/string performance, and you're more than welcome to comment and to run the test yourself and try and break as much as you can. Always happy for feedback. There's one last thing which was quite interesting with intrinsics, just a weird puzzle. So Intel had a machine at Intel. I did a performance course there, and afterwards they told me they had a machine where sometimes the equals method, no, sometimes the compare to method would come back with 0 on 2 different strings. So 2 different strings on that one machine would sometimes give back 0 when it was 2 different strings. Okay? And we actually got it down to a race condition between intrinsics and the normal, interpreted code, and when we turned off intrinsics, this was a very specific version of Java 8 running on a very, very specific machine. So it could have been a hardware bug, quite possibly, because then they upgraded the hardware and that bug went away, so we can never reproduce it again. That was quite a funny little race condition. So this is it from us. Thanks very much for listening. Thanks, Dimitri. And as I said, there's a surprise if you go there. If you don't, well, later on there'll be another surprise, not as good. Thanks. Any questions? We've got 4 minutes for questions. Lots of time. Yes, sir.
Some changes in Java 12 and Java 15?
Java, we've got in Java 12, it's no changes that we could detect. So Java 12 is the same as Java 11. They've got these what do you call those strings?
The intrinsics project. So the Amber, there are a couple of things that's going to happen to string. One is the string literals, where you can, like have 3 quotes open and then write free floating thing. That's going to happen, and a bunch of methods that relate to that. When, we don't know. Maybe 13, maybe not. They pushed it out of 12, so that might come. Other one is the string format and the original objects hash code. That's the Amber stuff. As I said, there is JEP 348 candidate state. It's not slated for release, so that's another thing that's going to happen. But other than that, string specific, I don't know. So there's 2 things.
I mean, the changes, as you know, from Java 7 to 8 were quite dramatic. And Java 8 to 9 is quite dramatic. Nowadays, it's like, every half a year, but the changes are not as big impact anymore. So I'm not sure what they'll do in the future.
By the way, is anybody using something other than 8, like past 8, 9, 10, or 11 in production?
Yeah, sure, of course.
You do have production.
Production, of course, yes, obviously. Obviously.
Okay.
Yeah.
So we have like 3 people, yeah.
Can't use Java 8 in production safely anymore, I don't think.
Yeah, no, you can't, yeah. OpenGDK. All right.
Right.
Thank you.
Thank you very much for joining.